Today we're going to continue our discussion of gases with something called the combined gas law. Now, the combined gas law is an equation really that's based on the concept of an ideal gas. Kinetic theory says that in an ideal gas, the particles have no volume, that's one of the tenets of that theory, and that they are not attracted to each other. When they have collisions, they're perfectly elastic. They're not attracted to each other at all. Now, neither of these two things are true about the gas. So in reality, there's no such thing as an ideal gas. So it kind of begs the question, why do we even study them if there's no such thing? However, real gases behave a whole lot like ideal gases under most conditions, normal conditions of temperature and pressure, and we can make great predictions about the way they're going to behave under those conditions. In the combined gas law, there's a couple of different forms of it, but we're going to include all four gas laws into the combined gas law. The first of these is called Charles' law. Charles' law is a law that relates or shows the relationship between volume and temperature. Now, one of the ways that my students in the past have come up with to remember that Charles' law deals with temperature and volume is to say that Charlie Brown is on TV. And if Charlie Brown is on TV, anytime we hear Charles' law, we're supposed to think of TV and we'll think of temperature and volume. And this is the equation that relates those two together. If we have an initial volume, V1, and a final, or an initial temperature, T1, then that's going to be proportional to a final temperature and volume for that same gas. When we look at that relationship, it's a directly proportional relationship, which means that when the volume goes up, the temperature goes up as well, or when the temperature goes down, the volume goes down. It's, again, called a directly proportional relationship because they both do the same thing. Boyle's law is the next one that we look at. Boyle's law involves pressure and volume. And my students, this one's kind of a gross one, but boils, they always say boils have pus and volume. Whatever it takes to remember it. Boils have pus and volume. And since it is kind of gross, we can remember that the gross one is the one that is inversely, it's the only one that's inversely or indirectly proportional. What that means is when the pressure goes up, the volume of the gas goes down, and vice versa. They do the opposite. They're indirectly proportional. And I expect you to be able to remember what the relationship is and whose law says what. So you need to remember that all of them are directly related or directly proportional except for Boyle's law. Guy-Lussac's law is the next one. And the way they always have remembered it is that guys like power tools. I'm saying girls like power tools also, but it doesn't fit with our little analogy. So we're going to keep with guys like power tools. This is another directly proportional relationship. So when temperature goes up, pressure goes up, and vice versa. Now, all of these laws are based on the fact that they're the only two things that are varying. For instance, if we're looking at Charles' law, then if we're looking at the relationship between temperature and volume, then pressure and the number of moles of the gas that are present in the container have to remain the same, or we can't make any determinations about how those two things are related. Same way here with Guy-Lussac's law. If we're going to relate or show the relationship between temperature and pressure, then we have to assume that the volume and the number of moles of gas are staying the same. And finally, we have Avogadro's law. Avogadro's law relates the number of particles and the volume. And those are both, again, directly proportional. If the number of moles goes up, the volume goes up. Now, just because the volume doesn't go, for instance, if the volume goes down, that does not mean the number of moles goes down. But that relationship will show you how it will change if we increase or decrease the number of moles of gas in that container. So that's Avogadro's law. And we're pretty much going to say, for lack of a better term for it, we're going to assume that anytime we have the number of moles in any kind of equation that deals with its combined gas law, we're going to say that it's Avogadro's law, just so we'll be able to give a name to it. And you'll see what I'm talking about in just a minute as far as that's concerned. So when we put all of these laws, and there are actually 4 of the laws, it says 3, sometimes we leave out number of moles, but I'm going to include that so that we can also use this equation to make determinations about that. But with these 4 laws, you can get the combined gas law. And that says that P1V1 over N1T1 is equal to P2V2 over N2T2. Okay, lots of variables there, but P stands for pressure, V for volume, T for temperature, and something very important about temperature that's going to mess with y'all's heads if you're not very careful is that it has to be in kelvins. Temperature must be in kelvins in order for this equation to work. And one of the most missed, or the thing that causes people to miss these problems the most, is not putting the temperature in kelvins. So watch out for that. N stands for the number of moles, like it always has. So those are the different variables that will be involved. Now, every time you see any kind of equation or a problem where we're going to need this equation, you're going to write down the whole thing first. Parts of this may not be used, and we may be able to simplify this equation because we can get rid of variables if they're never mentioned in the problem, or if it's mentioned that they stay the same. So let's look at this first example. It says the pressure on 5 liters of a gas decreases from 760 millimeters of mercury to 675 millimeters of mercury. What is the new volume of the gas? The first thing I want you to do, and it is not optional, is to circle what you're trying to find and label each of the other values with a variable that they refer to. So this is asking for the new volume of the gas, and the new volume of the gas is V2. So that's what we're going to be looking for, is V2, and I'm going to circle it because that's what we're looking for. The 5.00 liters is V1. 760 millimeters of mercury is P1, and the 675 millimeters of mercury is P2. So those are the only variables that are mentioned in this problem. And since only V and P, pressure and volume, are mentioned in the problem, we're going to be able to mark out N and T. So P1 V1 over N1 T1 equals P2 V2 over N2 T2. That's going to be written down in every single problem that you do. You have to write that down first, or you're going to lose points right from the beginning. So we just said that we can mark out N1 and T1 and leave behind P1 V1 equals P2 V2. As soon as we do this, I want you to name what the law that this applies to. And if it's pressure and volume, Cuss and volume, if you will, that's Boyle's law. So I want you to label off to the side on these problems whose law it is. Once we do that, then I want you to solve for the correct variable. So you're going to write the entire equation first. You're going to write the equation for the law that we're dealing with this problem, and then once more you're going to rearrange it to solve for the variable we're looking for. And since we're looking for V2, we're going to divide both sides by P2, which is going to reduce it to 1 or cancel it on this side. So the equation we're going to be working with is that V2 is equal to P1 V1 over P2. Now that you have everything labeled, if you've done it like I've asked you to, it makes it really easy to put the values in that you're supposed to use for the problem. So V2 is going to be equal to P1, which we said was 760 millimeters of mercury, times V1, which is 5.00 liters, over P2, which is 675 millimeters of mercury. If you'll notice, that's going to cancel millimeters of mercury, leave us with liters. And since we're looking for volume, that's a valid unit for volume. Multiplying and dividing and 2 sig figs leaves us with 5.6 liters. So that's the answer to the first problem. On to the second one. You're going to do the same thing. What I'd like for you to do is to pause this and go through and circle what you're trying to find, and then label each of the variables with the correct, each of the values with the correct variable in the problem. So if you did that, then hopefully you circled original temperature and realized that we're going to be looking for T1. That's what we're trying to find. At 250 degrees Celsius, when the temperature of a gas was raised to 250 degrees Celsius, that's our T2. The volume increased from 0.250 liters, so that's V1, and 1.20 liters is V2. So writing down our equation, P1 V1 over N1 T1 equals P2 V2 over N2 T2. We notice that we have been given values for temperature and volume only. So T and V, TV, hopefully you came up with the fact that this is Charles' law. And since only T and V were mentioned, we're going to be able to mark out P and N. And we're left with V1 over T1 equals V2 over T2. One of the hardest things to solve for on these problems, if not the hardest thing to solve for, is temperature, because people always solve for it incorrectly. Make sure when you're solving for temperature that you move it to the top first, or you're going to end up solving for the reciprocal every time. So if we're trying to solve for T1, the very first thing that I'm going to do is to multiply both sides by T1, which is going to reduce it to 1 or cancel it on this side, and we're left with T1 on top on the other side. That's critical to do at the beginning. If you don't do that, you're going to solve it incorrectly every time. So now in order to solve for T1, we're going to need to divide both sides by V2, which is going to cancel it over here. And we're going to need to multiply both sides by T2, which is going to cancel it on this side. Now there's a lot of variables there, but hopefully you're keeping track of what's going on, and what you end up with then is that T1 is equal to V1 T2 over V2. So that's the equation that we're working with, and since we have already labeled all the variables above, it's going to make it easy if we remember one thing. We've got 250 degrees Celsius up there, and if you put 250 degrees Celsius into this problem for T2, you're going to get a wrong answer. Hopefully you remember that we said in the beginning that we must have temperature in kelvins. So make sure that you take that 250 degrees Celsius, and the magic number, if you remember, is 273. When we add that, we get 523 kelvins. So make sure that's what you put into this problem. So T1 is going to be V1, which we labeled for 0.250 liters, times T2, which we said just now was 523 kelvins, divided by V2, which is 1.20 liters. Liters, notice, cancels. We're left with kelvins, which is what we want, and it's on top. That's critical. Make sure it's on top. If it's on bottom, you know you've done it wrong. So we've solved for kelvins. When we multiply and divide this, we get to 2 sig figs, 110 kelvins. Next problem. It says the gas left in a used aerosol can is at a pressure of 1.25 atmospheres at room temperature. And if this can is thrown into a fire, what's the internal pressure when the temperature reaches 927 degrees Celsius? So let's go through and do the process just like I showed you before. And I hope you're noticing that pretty much none of this is in green. So that means that you're going to have to put all of this down in your paper whenever you do these problems. Keep in mind that this set of notes is a quiz grade, so all of this set of notes has to be filled out just like I'm doing right now if you want that 100 for a quiz grade. So, looking at this problem, it looks like we're trying to find the internal pressure at the end, so it looks like we're looking for P2. So P1 is up here at our 1.25 atmospheres. Our T1 is up here at 27 degrees Celsius, and our final temperature, T2, is 927 degrees Celsius. And remind yourself what we have to do with those temperatures. Make sure you're thinking about changing those to kelvins when we get to that point. So let's write up our entire equation. We've got P1 V1 over N1 T1 equals P2 V2 over N2 T2. Think about what's been given to us for values, just pressure and temperature. Since we've only been given pressure and temperature, we're going to be able to mark out volume and number of moles. So the equation that we're left with is P1 over T1 equals P2 over T2. So if we're only using pressure and temperature, power tools, guys like power tools, Guy-Lussac. So this is Guy-Lussac's law. We're solving for P2. So all we need to do, it looks like, is multiply both sides by T2, which is going to reduce it to 1 or cancel it on this side. And we'll be left with P2 equal to T2 times P1 over T1. Plugging in those values, we get that P2 is equal to T2. Remember, we have to add 273 to this value, which is going to give us 1200 kelvins. We're going to multiply that by P1, which we said was 1.25 atmospheres, and divide by T2. Adding 273 to 27 is going to give us 300 kelvins. Our kelvins cancel. We're left with atmospheres, which is a valid unit for pressure. And when we multiply and divide this to 2 sig figs, we get that the pressure, the final pressure, is 5.0 atmospheres. Another example. It says we have a dry gas that has a volume of 235 milliliters at 15 degrees Celsius and 784 millimeters of mercury. If the volume expands to 600 milliliters and the pressure rises to 1500 millimeters of mercury, what would be the final temperature? So final temperature, T2, got another one of those temperature problems, so be careful. Those are the hardest ones to solve for, remember. So we're looking for T2. We're given 235 milliliters, which is V1, 15 degrees Celsius, T1, 784 millimeters of mercury, P1. Notice something also. Does it matter what pressure unit or what volume unit we use? And the answer is no. It can be milliliters or liters. It can be millimeters of mercury, atmospheres, kilopascals, torr. Doesn't matter, but temperature does. So make sure you're converting that temperature. So if the volume expands to 600 milliliters, so there's our V2, and the pressure rises to 1500 millimeters of mercury, there's our P2, and again we're looking for T2. So Our equation, P1 V1 over N1 T1 equals P2 V2 over N2 T2. Words wanting to work a little slow. Hopefully you'll hang with us till the end. We never mention number of moles. That's the only thing we don't mention. If that's all we don't mention, we're dealing with pressure, volume, and temperature, all three. We're going to call that the combined gas law. Combined gas law. So, looking for the final temperature, T2, remember what we said. Move that to the top first. So we're going to multiply both sides by T2. I'm going to cancel it on this side. And now we're going to multiply both sides by T1 to get rid of it over here because we're trying to solve for T2. So multiplying it on this side will cancel it. I'm going to put it over here. We're going to divide both sides by P1. We put that on this side, it's going to cancel it on this side, divide it on this side. Divide both sides by V1, it will cancel it on this side, put it on this side. So let's see what we've got left over. We've got that T2 is equal to P2 V2 T1 over P1 V1. Lots of variables, but if you keep track of them and the fact that they're already labeled up in the problem, it really does make it much easier to put them into the problem. So let's do that real quick. I'm going to change colors so it'll hopefully stand out a little bit. T2 then is going to be equal to P2. We said P2 was 1,500 millimeters of mercury. V2, we said V2 was 600 milliliters. T1, 15 degrees Celsius. Make sure you add the 273. When we add the 273, that gives us 288 kelvins. And now divide that by P1, which is 784 millimeters of mercury. Be careful, if that were in atmospheres, for instance, make sure you change that unit so they match. Doesn't matter what unit it is, but they both have to be the same, so be careful of that. And then our value for V2 is, or excuse me, for V1 is 235 milliliters. All the units that cancel are millimeters of mercury and milliliters, and we're left with kelvins on top, which is a valid unit for temperature, so that's good. When you plug this in your calculator, guys, be careful, because make sure that you're plugging in 1,500 times 600 times 288 divided by 784 divided by 235. Make sure you put that in your calculator. Your calculator's stupid. It doesn't know what you mean. It just knows what you put in. So make sure you're always dividing by what's on bottom. When you do that, to 2 sig figs, you end up with a temperature equal to 1,400 kelvins. Okay, I know this is a lot of calculations to do, but each one of these has shown you something a little bit different. And this is really the only way we can do it to effectively learn how to do these problems, is just to show examples of each of those situations you can come across. Okay, one final problem. This is going to kind of throw everything and the kitchen sink at us, I think. So look at what it tells us. This is our first one that involves moles. It says we've got 0.0473 moles of dry gas that has a volume of 1.25 liters at 100 degrees Celsius and 880 millimeters of mercury. Okay, so we already have N1, V1, T1, and P1. And it asks us what the volume would be if the amount of gas is increased to 0.662 moles, so there's our N2, and remeasured at STP. Okay, it has been a while since we talked about STP, but it's a good time to bring up what it is because it's most applicable when we're studying about gases. STP, remember, is standard temperature and pressure. And standard temperature and pressure are 1 atmosphere and 0 degrees Celsius. Well, for us, usually the most useful way of referring to this is 760 millimeters of mercury for the standard pressure and 273 kelvins. So there's our standard temperature and pressure for gas laws. So that's going to be, anytime they give you STP, that's going to be one of your temperature and pressure values. For us this time, it's going to be P2 and T2. So those are our final values. And look what it gives us. It really throws everything at us. We're looking at our equation, P1 V1 over N1 T1 is equal to P2 V2 over N2 T2. It gives us all of it. So we are going to be using all of the variables, and since moles are involved, for lack, like I said, of a better term, instead of calling it combined gas law again, Avogadro's law is the only one that involves moles, so we're going to call this Avogadro's law. If y'all write down avocado, I don't know what I'm going to do. Avogadro's law. Okay, so what are we solving for? We're solving for the new volume, so we're solving for V2. So fortunately it's already on top, so we don't have to worry about that. So what are we going to do? We're going to divide both sides by P2. It's going to cancel over here and show up on the bottom over here on the other side. We need to multiply both sides by N2, which is going to reduce it to 1 or cancel it on this side. It's going to show up over here. And finally, we're going to multiply both sides by T2, which means it's going to cancel over here and show up on top over here. So if I can squeeze all of that in. Okay, what does that leave us with? It leaves us with V2 equal to N2 P1 V1 T2 over P2 N1 T1. Wow. So lots of stuff there. But we've got it all labeled, so let's just plug and chug it in. We've got V2 then equal to N2 0.662 moles. I hope I don't run out of room. If I do, we're going to squeeze it in somehow. P1 is 880 millimeters of mercury. V1 is 1.25 liters. I'm going to write even smaller. And T2 is, I've lost it, there it is, 273 kelvin, so it's already changed for us. That's going to be over P2. P2 is our 760 millimeters of mercury, our standard pressure. N1 is 0.0473 moles. And T1 is, let's see, 100 degrees Celsius, so that's going to be 373 kelvins. Wow. So let's look at what cancels. We've got moles canceling. We've got millimeters of mercury canceling. We've got kelvins canceling, and we're left with liters, and we pray that it is a valid unit for volume, and it is, and it's on top. So we must have done something right. So when we divide this, be careful how you put it in. 0.662 times 880 times 1.25 times 273 divided by 760 divided by 0.0473 divided by 373. And when we do to 2 sig figs, we get 15 liters. And